Hello, welcome to Easy Math. My name is Zishan, and today we're going to look into sketching of exponential and logarithmic curves in additional math IGCSE. There are supposed to be equations of this form that you're going to be asked to sketch. I'll show them to you. There it is. This is the form there's going to be for exponential curves, and this is the form there's going to be for logarithmic curves. There are 4 points in each of them that you would want to keep in mind while you're sketching them: horizontal asymptote and vertical asymptote. Basically, asymptotes for these curves. Then there is x-intercepts, y-intercepts, and the shape they're going to be. 4 points: asymptotes, x-intercept, y-intercept, and the shape they're going to be. These 4 points, once you have plotted them on a grid, and one random point, so that's supposed to be a part of our shape thing only. One random point will take one random x value and obtain the y corresponding to it. Then we sketch a x comma y, a random point on our grid. So these four should be enough to figure out what the curve is going to look like. But before we dive into the uh, points that you want to keep in mind, I would like you to see something about these curves. Let's start with mm, a logarithmic curve, maybe. Oh, an exponential curve. Let's start with an exponential curve. There it is. I have n Desmos put in the equation of the curve. K e to the power of nx plus a. That is the form I'm going to get. As of now, I have put up a k equal to 1, n equal to 1, and a equal to 1. Let's see what the curve looks like. Well, this is what it looks like there. See, the red thing. And I would like you to notice something about this particular curve. Don't you see there is one boundary kind of a thing that the curve has? It's gonna be at y equal to a. Do you see that line? See, look at that. The curve looks like it is meeting that particular boundary, but whenever you zoom, you'd see it never actually does. If you zoom in, you'd see it never actually does it. Huh? Let's zoom in somewhere close, maybe. See, look at that. Well, that boundary is known as asymptote. This equation, y equal to a, out there on the left, that is known as an asymptote to this equation, to this curve. You'd see as I move, change the values of a, this line also moves with it. And the entire curve looks like it's never going to cross the boundary. Look at that. Look at that. Now, although with the value of a, the curve changes its location, but the line stays as a boundary there at y equal to a, y equal to 4.1 in this case. That's an asymptote. How do you find the asymptote? Well, that's a thing that we're going to discuss right now. But I would like you to know this happens to be the first point you would keep in mind while you're sketching an exponential curve. Now, let's see why do we have an asymptote at that particular place. How about we take an example? 2e to the power of 3x plus 4 maybe. Okay. Now, let's see what happens to the value of y when x happens to be a large negative number, as large as a negative infinity. Let's see. Y equals 2e to the power of 3 negative infinity plus a 4. I know this can be written as 2 by e to the power of 3 into positive infinity, and negative index can be converted to a positive index if I take e down in the denominator, plus a 4. Well, there's something about e to the power infinity that we should know. This tends to be a very large number. E raised to a infinity, it's a very large number. Divide 2 by this large of a number, this whole thing becomes as small as a zero. Very, very little it will become. If you divide 2 by a very large number, what you're seeing is when x tends to negative infinity, y tends to be a 4, a 0 plus a 4, a 4. And that is why when we sketch the curve, you'd actually see for very large values of x, maybe which are somewhere here, negative infinity, somewhere there, you'll see that the y value comes out to be around a 4 there. And that is why the curve looks like it's about to go meet this line, the y equal to 4 line, at very large negative numbers on x. That is what an asymptote is like. It acts like a boundary, and the curve doesn't go beyond that boundary. So that was the first point you wanted to keep in your mind. It's about the horizontal asymptotes of exponential curves. It's always supposed to be at y equal to a. In this case, it's a 4, y equal to 4, when it is a k e to the power of nx plus a. There it is. A is a 4 for us. K is a 2 for us. N is a 3 for us. Y equal to 4. Now, second point. It's about the x-intercept. Remember, whenever you want to spot the x-intercept of a curve, you're supposed to substitute a y equal to 0 into the equation and solve for x. In this case, 2e to the power of 3x comes out to be a minus 4. E to the power of 3x comes out to be a minus 2. Well, there is no x which can satisfy this equation. E to the power of 3x can never be a negative 2, whatever be the value of x. In a way, there is no x-intercept, for this particular curve. But if you want to generalize it, 0 equal to k e to the power of nx plus an a. Let's obtain the location of, maybe let's obtain the value of x-intercept generally. In this particular case, yes, there was no x-intercept, but let's see. So there it is. I have substituted a y equal to 0, equated it to the whole thing, k e to the power of nx plus a. Let's solve for x. K e to the power of nx equals minus a. There it is. E to the power of nx is a minus a by k. Let's take natural log on both the sides. E to the power of nx equals ln of negative a by k. There it is. Nx ln e equals ln negative a by k. And there nx, well, this is always a 1, by the way. Nx is ln negative a by k. X is 1 by n ln negative a by k. That's the form of x-intercept for any exponential curve. There. Now, whenever a and k are positive, ln of negative a by k, this particular part is not going to be defined. There's going to be no x-intercept to the curve in that case. Now let's look at the third point, the y-intercept. Y equal to 2e to the power of 3x plus of 4 is where we are. We're going to have to substitute x equal to 0. If you want to find the y-intercept of any curve, substitute a y x equal to 0. You will get the y-intercept. There it is. 2e to the power of 3 times 0 plus a 4. That's a 2e to the power of 0 plus a 4. That's a 2 plus 4. That's a 6. You will see whenever there is a equal to k e to the power of nx plus a, substituting a x equal to 0 gets you to a k e to the power of 0 plus a which is a k plus a always. That again is the general form of y-intercept for an exponential curve. And now comes another place of importance. It's about the shape of the curve. Okay. Now that we have first the horizontal asymptote, y equal to 4. Second, we have the x-intercept, which there was no actual x-intercept for this one. No x-intercept. And third point is about the y-intercept, which came out to be y equal to 6. So the place where the curve would cut through on the y-axis would be a 0, comma 6. And fourth point, it's about the shape. For the fourth point, I would highly recommend obtaining the value of y at some random value of x. Let's say x equal to 2 maybe. So y equals to 2e to the power of 3x plus a 4. And that's going to be 2e to the power of 6 plus a 4. When you substitute x equal to 2 here, comes out to be e to the power of 6. What will that be? 3 to the power of, around a 3 to the power of 6. That's a huge number. Let's just see. E raised to a 6. 403 into 2 plus a 4. It's a 810. That's a large number. So 2 comma 810 is also going to be seen on our curve. Okay. Although I won't be able to go to a 810 on the y, but we will try to make sure that it makes a little sense with that point in perspective. I'll show it to you. Look at that. I'll draw the curve now. There it is, your y-axis, your x-axis. Now let's locate the horizontal asymptote. There it is, y equal to 4. Now I know back curve is not gonna cut through the um, asymptote. So there it is, my asymptote. Now let's bring in your y-intercept. It's a 0, 6. And at x equal to 2, somewhere here, the curve, which is a very large value on y, maybe somewhere there it's gonna be. Well, it's a 2 comma, let's use a different color. Let's do a 2 comma 810, somewhere there. Huh? So there it is. Your entire curve will look like it's about to meet this asymptote, go past through the y-intercept, and go up like that. There. That's your curve. Y equal to 2e to the power of 3x plus a 4. Well, there might be a little more to this exponential curve than what we have just seen. And I'll tell you where this complication is. When y equal to k e to the power of nx plus a and k or n or both of them happen to be negative, that's where this curve looks a little different from what we are used to. That this is what we are expecting it to be, but it looks a little different. Now the difference I won't tell you as of now. We will first look at some example and come to some conclusion about it later on. Let's take some example. Y equals to negative 2. I'm taking k as a negative number here, and a 3x plus a 4 maybe. Okay. And the same thing. First, we'll locate the horizontal asymptote. It's going to be y equal to 4. Second, x-intercept. Let's see. X-intercept is when y is a 0. So you go negative 2e to the power of 3x plus a 4. And there it is. Negative 2e to the power of 3x equals a minus 4. E to the power of 3x comes out to be a 2. 3x ln e comes out to be a ln 2. If you take natural log on both the sides, 3x comes out to be a ln 2, or x comes out to be a 1/3 of ln 2. There it is. Now we have some x-intercept for this curve. Okay, third point. It's about the y-intercept. Substitute a x equal to 0. Comes out to be y equal to k plus a. In this case, negative 2 plus 4. It's a 2. There it is. Substitute a x equal to 0 basically. Okay, done. And now about the shape. I told you for the shape, take one random point, maybe at x equal to 2. Check it out. Y equals to negative 2, e to the power of 6 plus a 4 comes out to be a negative 810, negative 806. So there it is. At 2, it's a negative 806. How to spot that number now? So let's see. Hmm. Let's locate all the points that we have and figure out what the shape would be. Hmm. Let's have some space for the sketch to be drawn there. Now let's have the horizontal asymptote. It was at y equal to 4. There it is, y equal to 4. Then we have the x-intercept, which is a 1 by 3 ln 2. 1 by 3 ln 2 would be somewhere there. Let's say 1 by 3 ln 2 comma a 0. And y-intercept was a 2. So this is y equal to 4 line. So 0 comma 2 is going to be observed somewhere there. And I also know that at a 2, x equal to 2, y happens to be a very large negative number. It's somewhere there, very large negative number. So there, 2 comma negative 806, somewhere around that. This is an approx value, by the way. One mistake I see, I have spotted the x-intercept wrong. It is on the negative x-axis here for me, but it's supposed to be on the positive x-axis. So it's going to be somewhere here. 1 by 3 ln 2 comma a 0. That's where it would be. Hmm? So there it is. All points spotted. There it is. There's this one. Would be down here somewhere, roughly the x-intercept, y-intercept, and the asymptote. Don't you think that gives you an idea of what the curve may be like? There it is. This acts like a boundary. Of course, I can't go this far, and I'm gonna have to go a little close. There, comes down, passes through the y, and then through the x, and then through that value. There it is. There is your curve. Done. So of course, for negative value of k, this is what the curve looks like. For a negative value of a, negative value of n, a similar change would be observed, but I would like you not to memorize it. Instead, I would like you to simply spot y-intercept, x-intercept, and one random point and the asymptote, and simply go join them by a smooth curve instead of memorizing what it would be. What actually happens to these curves is a part of transformations, which is not a part of your syllabus. Where transformations to the curve, that's a thing in HL, IB, HL. So you are not supposed to know about them. Simply join them by a smooth curve once you have spotted the points. Although on this sheet, I have roughly drawn what the curves would look like if k is negative, the green one. If both k and n are negative, this is what it may look like. If only n is negative, this is what it will look like. And if k, n are both positive, this is what it will look like. That's the first one we drew. Huh? But again, like I told you, follow the points and it will make sense. And now we're going to move into logarithmic curve. This is the general form of the equation you're gonna get to sketch in additional math. And again, vertical asymptote to this curve is a thing. Again, before we know and learn x equals to minus b by is supposed to be the vertical asymptote, we'd like to see what it means. So I'll take you to Desmos and we'll sketch it there and see. And there you see is an logarithmic curve that I have sketched. Look at that. I have substituted the values of k, a, and b. Oh, why do I have a b there? Give me a second. Do we actually have a b? Yes. So there's supposed to be a b. Okay, so you go, look at that. Again, do you see a vertical kind of a boundary happening there? Yes. How about we watch what that is? Minus b divided by a. And again, it's a vertical line at x equals to minus b by a, which happens to be the boundary for this particular curve. Let us move the value of b. You'll see that the boundary moves with it. Let's move the value of a. Again, the boundary moves with it. But the question is why? Why do we have a boundary like that? So let's watch. Let's take up an example where k is a 2, a is a 3, b is a 4. Well, let's figure out the value of y when 3x plus 4 is a 0. Okay, let's see. Y equals 2 ln 3x plus 4 is a 0, so 2 ln 0. Okay, 2 ln 0 is not defined. And what will that be actually? Let's see. So, in the previous example, we saw e to the power of negative infinity tends to be a 0. Let's take natural log on both the sides. And there it is. I get a rough value, that is a 1 by the way. I get a rough value that ln 0 tends to be a negative infinity. So now you know when x is a negative 4 by 3, meaning 3x plus 4 is a 0, x is a negative 4 by 3, right? Take the 4 to the other side, 3 down here in the denominator. When x is a minus 4 by 3, y tends to be a negative infinity. And that is why you have a vertical asymptote at x equal to minus 4 by 3. The point is, when x becomes a minus 4 by 3, y becomes a very large negative number. And you can actually see that happen on the curve. Look at that. I'll remove the boundary. Look at that. Right when x approaches a value of minus 4 by 3, look at that. It's not letting me go down there. Oh, but you can see at negative 4 by 3. Oh, oh, I think it needs to have that thing fed, right? X, y equal to 2 ln 3x plus 4. 2 ln 3x plus a 4. Now let's get rid of this curve and let's substitute our x equal to minus 4 by 3 in here. And let's look at the value. Look at that. Right when you have the curve approach, why is it not letting me go below that? Oh, yeah, it does. Okay, okay, okay. Slowly it vanishes. Huh? You see, I'm reaching a negative 4 by 3 on x and negative 1.33, and y becomes a negative 9.79. If I go further, closer to 4 by 3, negative 4 by 3, the y value will shoot down to a very large negative number. There. Well, Desmos glitches a little around that asymptote thing, but yeah, there it is. That's your guideline. There it is. That's your guideline to the curve. X equal to minus 4 by 3. So that's your location for the vertical asymptote of logarithmic curves. When y equals to k ln ax plus b, we took an example 2 ln of 3x plus 4. We saw that the vertical asymptote is supposed to be at x equal to minus 4 by 3. On a general basis, it's going to be x equals to minus b by a. Okay. Now let's look at the x-intercept. Well, x-intercept is always supposed to be when y is a 0. So there it is. We're going to substitute a 0. 0 equals to 2 ln 3x plus 4. There it is. 0 divided by 2 is a 0. 0 equals to ln 3x plus 4. To get rid of the log, e to the power of 0 is a 3x plus 4. The base of e raised to a 0 should be 3x plus 4. And there it is, 3x plus 4 is a 1. E to the power of 0 is a 1. X comes out to be 1 minus 4 divided by 3, or a minus 1. There it is, your x-intercept. On a general basis, the x-intercept would be 1 minus b divided by a. There it is. Okay. Again, obtained by substituting y equal to 0. Third thing, the y-intercept. Y-intercept is when x is a 0. Let's substitute y equals to 2 ln 3 times 0 plus a 4 comes out to be 2 ln 4. There it is. That's your y-intercept. And the fourth thing about the shape. So shape, like I told you, take one random value of x, maybe a 2. Y comes out to be 2 ln of 3 into 2 plus a 4. There it is, 2 ln 10. And let's see what that is. 2.3 into 2 comes out to be a 4.6. There it is. So 2 comma 4.6, or a 2 comma ln 10 is also going to be one of the points our curve passes through. Okay, so we have all the points now. We're going to go sketch this thing out. Let's see. This is our entire thing. We're going to do it on the left here. We're going to do it in the left here. So there, your y-axis, x-axis, you go locate our mm, vertical asymptote. So there it is, a minus 4 by 3. X equals minus 4 by 3, serving as a boundary for our curve. And there it is, x-intercept is a minus 1. So somewhere there is where it would be, minus 1, 0. The y-intercept would be a 2 ln 4. 2 ln 4 would be somewhere here maybe. And at x equal to 2, we are expecting a 4.6. So somewhere there. Now that we have 3 points and the asymptote 1, 2, and 3, and the asymptote, we know what the curve is going to go like. There it is, your boundary, and that's your curve. Y equals 2 ln 3x plus 4. There, done. Okay. Now, another complication to this arrives when you have k lesser than 0 and a lesser than 0, or a lesser than 0. So both of them are going to bring in a complication. What complication? The curve is going to be flipping about the asymptote, flipping about the x-axis, something like that. So again, like I told you, spotting the points is good enough. Let's take one example. Y equals 2 ln minus 3x plus 2 maybe. Okay. So again, we go first point. Let's see. Y equals 2 ln negative 3x plus 2. First point, your vertical asymptote. X equals to minus b by a. B in this case, if you compare it with k ln of a x plus b, k is 2, a is minus 3, b is 2. In this case, it's a negative 2 divided by negative 3 comes out to be 2 by 3. There, done. Now let's look at the x-intercept. X-intercept is when y is a 0. There it is. Let's substitute. 0 equals 2 ln 3x, oh, negative 3x, negative 3x plus 2. There. So 0 equals ln negative 3x plus 2. E to the power of 0 equals negative 3x plus 2. 1 equals negative 3x plus 2. Negative 1, negative 1 minus 2 is a negative 3x. So minus 1 by minus 3 is a x. There it is. Or a very simple x equals to 1 minus b divided by a would have worked. 1 minus b divided by a, that is a minus 1 by minus 3. Again, there is your x-intercept. Okay, that is the second thing. Let's look at the third thing. It's the y-intercept. Y-intercept is when x is a 0. Let's see. 2 ln negative 3 into 0 plus a 2 comes out to be 2 ln 2. There it is, your y-intercept. Okay. Now let's look at the shape of it. For the shape, I'm going to take a x equal to 2 and y in that case comes out to be negative 3 into 2 plus a 2 comes out to be 2 ln of negative 6 plus a 2. That's a 2 ln negative 4. Well, that's not a defined thing. Let's look at x equal to minus 2 maybe. Y equal to 2 ln negative 3 into negative 2 plus our 2 comes out to be 2 ln of negative 3 into negative 2. That's a plus 6 plus 2. There it is. A 2 ln 8. 2 ln 8. It's a positive number. Of course, what I saw is when I substituted x equal to 2, it gave me a negative value there, negative value of logarithm. No, logarithm of negative value is not defined. So what I did is I took a negative 2. In that case, I know these two are going to multiply, give me a positive number. I, a very, being a little clever, I chose x equal to negative 2 here in this case. And the y-intercept and the point corresponding to it actually, and at the y corresponding to it came out to be r2 ln 8. There it is at a negative 2. Okay, now that we have 4 points, we're going to go sketch. Let's see. There it is. Your y-axis and the vertical asymptote at x equal to 2 by 3. Let's see. There it is, your x equal to 2 by 3. And then the x-intercept was 1 by 3. 1 by 3 is going to be here somewhere. Okay. 1 by 3 comma a 0. And I also know that the y-intercept is a positive number, 2 ln 2. And I also know at a negative 2, this guy is a 2 ln 8. So somewhere there it will be. And with those points in place, like I told you, 1, 2, 3, and the boundary in place. Don't you see the curve, man? Look at that. There it is, your curve. Of course, I can't be this accurate. I'll try. There. There is your curve. That's what it'll look like. That was a y equal to 2 ln of negative 3x plus 2. And again, with k being negative, which means this particular thing, well, it's your job to figure it out. What I do now is I give you some questions, you try them out for exponential and logarithmic sketching and come back to me. Let's see. Tell me if they don't make sense. Well, these are the questions. These are the questions that I would like you to try. Huh? I would like you to go specially for this one, a regular kind where all three of them are positive. Huh? Maybe this one, this one, this one, and maybe this one. Take a screenshot, try these questions out, draw them, and of course you can use Desmos. Write yourself the equation there, 2e to the power of x minus 4 maybe for this one, just to see how what Desmos tells you it looks like, and check the asymptotes and all. There, take a screenshot. You have to do these questions, okay? That's it for logarithm and exponential sketching from additional math. There's not much to it though, besides what we have discussed. Of course, there are a lot of things one would want to discuss with these, but that is for later, not right now. Okay, I'll see you. Bye bye. Bye bye bye.